Right, sounds like we're live. So good afternoon. Welcome to this talk on the challenges of embedded Linux. So you probably know that I'm an embedded Linux guy by now. I've been doing stuff with Linux and embedded devices for 20-something years, a long, long time anyhow. And this is kind of about, well, first of all, what is the difference between a normal computer and an embedded computer? So normal computer on the left, it's got a screen, it's got a keyboard, some kind of processing unit. That's basically it. All computers are the same. All normal computers are the same. But on the right, embedded computers, they are a wide range of different sizes and styles. We have Wi-Fi routers, we have smart doorbells, we have smart thermostats, we have TVs, we have car infotainment systems. So these are all embedded Linux things. So I meant to ask this earlier, actually. Anybody here use embedded Linux so far today? Today? I mean, technically, if you've connected to the Wi-Fi, you probably that's running Linux. Coffee machine. I'm not sure that's sophisticated enough for Linux, but we can see. Android, yep. Android is very much an embedded Linux operating system. So yeah, you end up using this thing every single day. So what's special about embedded? Why am I making a big fuss about this? So the first thing then is that building embedded devices is very cost sensitive, or at least in most industries. So most people starting out with this, they will come up with a spec and they say, well, we need a computer to make this work. It's easier and cheaper if we design the computer. Oops. Low power. Most embedded devices, well, they have to run for long periods of time, maybe 24/7. So we don't want to use up too much power. Also, if they're running on batteries, then we definitely don't want to use too much power. So that's the kind of Android case. Low thermal footprint. Basically, we don't want any fans in our embedded devices. We don't want a fan buzzing away in our doorbell or smart thermostat. We want it all nice and quiet. And size matters. So these things generally have to fit in with maybe a domestic environment or an industrial environment. But size, yeah, they've got to fit in the right case. Maybe they've got to be aesthetically pleasing. So basically, you can't just take a PC and expect that to work. And longevity, some of these things are expected to run for many, many years without rebooting. So things like Wi-Fi routers, TVs, they basically never ever get turned off. They just sit there and work the whole time. So my emphasis here is on Linux as an embedded operating system. So why Linux? So Linux is a good choice for the reasons given here. The key one really is complexity. Way back, you could drive one of these things with a simple RTOS, but increasingly things are getting more and more complicated. There are many communication stacks, more complicated graphical environments and so on. So you need a full-sized operating system to do all of these things. So Moore's law is kind of pushing Linux into the embedded here. It's free, which is nice. Free in the sense of freedom, meaning you get the freedom to modify and study the source code, which is good. Linux is very functional, so it supports pretty much any bit of hardware you can throw at it. It has a 10-week release cycle, which means it's always pretty much up to date. And it's also free in the sense that you don't have to pay for it. So altogether, these make it a very attractive operating system. The note at the bottom is saying that, of course, Linux isn't suitable for every application, particularly if you have really cheap devices running a little microcontroller, then that's not going to have the memory or storage to run Linux. So My estimate is a few tens of dollars, so something costing maybe $50 and upwards is capable of running Linux. Less than that, maybe it isn't. Okay, so I have 5 challenges, which I've selected more or less at random, and I'm going to go through them one by one. Okay, challenge number 1, hardware compatibility. The big dark secret of embedded. So we don't want to use standardized PC-based hardware in embedded systems for all the reasons we've discussed. It's too expensive, it's too noisy, it takes too much power. So the obvious thing to do is to design your hardware specific for the task. Good idea. Kind of. Except that it means that each device becomes an island. So every device has unique hardware constraints. They are designed and built in unique ways. And consequently, they're hard to develop code for because you need a dedicated development environment. And yeah, updates are quite tricky, especially given that manufacturers are often not that interested in doing the updates once you've come to the end of your license. Here's my generic diagram of an embedded thing. For those of you who are in my Yocto hardware workshop, this is quite similar to what we actually did in that workshop. So in that case, the main CPU board actually was a Raspberry Pi, which is not the obvious choice, but it works. And then on the left-hand side, we have inputs, so GPIOs, buttons and such like. Maybe a camera. CSI is a camera interface. Maybe other things which I haven't missed to put on the diagram. And then on the output side, we need to output various things. So I2C, in this case, connecting to a multicolor LED. So you make your LEDs flash in different colors. Cool. Or you can use good old GPIO and just turn a regular LED on and off. And many things these days have some kind of display. So on the right-hand side, we have MIPI DSI. DSI is the most commonly used display interface on embedded devices, much cheaper than HDMI. Up there at the top, we have debug ports. So you need to debug these things. And usually where the place we start off is with, first of all, with the serial console, hence RS-232. If you want to do a little bit of low-level debugging, you might be using JTAG and some kind of trace device to trace at low levels. That's especially useful when you're doing the initialization and board bring up, and you want to get the bootloader to work correctly, and you need to understand some things about that. So we have some debug ports. And then down at the bottom, we have the communications. So typically Wi-Fi, Bluetooth. Oh, and eMMC, embedded MMC memory. That's the flash memory most often used for storing stuff on embedded devices. So I guess my point here is that an embedded device is quite a lot different to a regular normal device. So, yeah, how do we cope with the lack of hardware compatibility? So let's look at developing the code. First, an obvious thing to say is that you can't do native compilation on your typical device. You can just about do this on a Raspberry Pi, but generally speaking, the target devices are locked down. They don't have the right power to actually compile anything. And you'll be using a different operating system on the target device than what you use in your development system, so it's definitely not going to be Windows. It might be Linux of some kind, but it will be a different kind of Linux. Conclusion then, we're going to have to cross-compile. Almost all embedded development involves cross-compiling on some development machine and then creating images that we can put onto our target machine. So cross-compiling. A quick single slide on cross-compiling. This is using GNU GCC. There are other compilers such as Clang, but I'm focusing on GNU because that's what most people use. So GNU has this rather weird idea that the cross-compilers have this prefix, Arch Vendor Kernel Operating System. So a good example of that would be for a 64-bit ARM computer. So the Arch is AArch64, which stands for ARM architecture, 64 bits. The vendor in this case is Buildroot, because I use Buildroot to build the toolchain. The kernel is always Linux in my examples. And the operating system we normally set to be GNU, because we're probably using some GNU components in here somewhere. So with all that information, we can run our cross-compiler using the big long name minus the GCC, and we're going to compile a single C source file and produce a single binary. And we can show that it's been cross-compiled. If you use the file command, we can see that hello ARM is an ARM architecture 64. Okay, so it's not going to run on my PC. It's only going to run on the target device. So building the operating system for the target device is more than just compiling the odd program here and there. So how do we build an operating system? Well, we need to. To start off with, we need a toolchain. Until you've got a compiler, you can't really do anything. Typically, the toolchain is built from source code, but you can also download pre-built binaries and use those. So we need a toolchain. Then, using that toolchain, we can compile the bootloader code to initialize and configure the target board. Every target board has its own specific bootloader, which is different to all other boards, unfortunately. Likewise for the kernel. You're going to have to configure and compile the kernel specific to the hardware that you want. And even if the kernel's the same, the device tree, which I'm not got any slides on, but alongside the kernel, you need a device tree. The device tree explains what to the kernel what the peripherals are and what addresses they're at. So there is some customization to be done here. Then when you've done all that, you need to build all the various daemons. So at the very least, you need an init daemon to start the whole thing off. And typically you need network daemons, login daemons, daemons for all kinds of things. The init daemon is typically systemd these days, but you can use other init daemons if you wish. And you need to build all the dependencies of all that stuff. So especially libraries, but also configuration files and scripts, all kind of stuff needs to come together to make a working Linux operating system. And then when you've done all that, you need to create an image. You need to put all this all together into a format that you can put into the flash memory of the target device. So back in the old days, like 10, 15 years ago, we actually had to do all this by hand. So typically, if you go back to the mid-2000s, we were kind of hand compiling stuff. We'd have a combination of some scripts and some manual steps. It was kind of fun the first time you do it, but the third or fourth time it gets a little bit boring. And this is known as roll your own, or RYI. So look, thankfully, we have moved beyond roll your own operating systems. Order from chaos. So we have two tools in particular. We have Yocto Project and Buildroot. And they basically take all the hardware work out of this. They allow you to specify what you want to build using recipes or configuration files and make files in the case of Buildroot. And then you just type make or something similar, and it goes away and chugs away for some hours usually to create the entire operating system from scratch for you. And it's doing this mostly from upstream source code. Yocto Project is probably the most commonly used. It is sponsored and supported by Linux Foundation. And they've done also a very good job of marketing Yocto Project. So most people working in the embedded space have heard of Yocto. Most SoC vendors like Qualcomm and Rockchip and MediaTek have board support packages for Yocto Project. So it's the default place to go. Excuse me. A friend of mine who is actually an advocate for Yocto Project, he likes to say that the world runs on Yocto. It just doesn't realize it. Also, I'm going to mention Buildroot. So Buildroot is, well, a lighter touch, as it says on the slide. It doesn't require so much investment in time and I would say time and space, in time and effort to understand how it works. So it's great for people working in smaller teams, but it doesn't scale particularly well to large teams. Also, without the support of Linux Foundation, it is not so well supported. And so, yeah, it doesn't have quite the same traction as Yocto does. Nevertheless, Buildroot is used on a fair number of embedded processors that you will be using from time to time. Oops. Okay, so developing the code is complicated, but build tools like Buildroot and Yocto Project get us out of that particular hole. What about updating things? We'd like our things to be updated. Typically, OEMs want to, or should, update devices, maybe with new features, certainly with security fixes and so on. But again, this is a difference between the way embedded systems work and regular normal computers work. So in your normal computer, running, for example, Linux, typically you do the update using RPM or deb apt install or something. Doesn't work on embedded systems. The problem with package managers like RPM and deb is that they are not atomic. So you give it a bunch of packages to update, but it does them kind of one by one. If the update fails for some reason, for example, because somebody pulls the plug out, or you lose connectivity because somebody, the Wi-Fi stopped working, then you got a problem. Typically, you lead to what I call here an inconsistent state. An inconsistent state generally means your device is bricked, and we don't want bricked devices. So RPM and deb, no, we don't use them. Instead, we can update the entire system image in one go. So we treat the root file system and any other components as a single entity. We update the whole thing in one go. This can then be made atomic. Either we did the update or we didn't do the update. It's easy to differentiate. So we generally use a mechanism called AB update. Essentially, we have two copies of the operating system. We have one copy in the A slots and another copy in the B slots. And both are complete operating systems. So initially, once you've first flashed your device in the factory, you're going to be booting from the A slots. Then you get an update coming in, you write the update to the B slots, which are not being used at the moment. And once you've done the write, you can verify it, so you can know for sure whether the update was valid or not. Then you throw a switch in the bootloader, a software switch, so that when you next reboot, you'll boot from the B slots. Therefore, you're booting the new operating system. You can get cases where the new operating system doesn't work for some time, so it doesn't boot correctly, in which case there are timeouts and retries in the bootloader. So after some number of retries, it will fall back to using the last known good operating system. So if the B operating system for some reason won't boot, we fall back to using the A version. And then you're going to have to update the B slots over again, hopefully with a version which actually doesn't have whatever bug was causing you to have problems. These updates, they often come through over-the-air or through network connections, as we call them OTA or over-the-air updates. But you can also do it on a more informal way, just by going around with a USB stick and running the updater locally. So it depends on the volume. But I'm sure in many organizations, you have the man with the USB stick with a version that works, and he'll kind of go around and apply it to all the various, I don't know, security cameras or whatever. So we have a whole bunch of AB updater mechanisms supported by both Buildroot and Yocto. So I've chosen 3 here, which seem to be fairly commonly used. There are others. There are dozens. But software update was one of the first. It's pretty robust. It's been used a lot. RAUC, I had to look this up. RAUC stands for Robust Auto Update Controller. I found that not obvious. Anyhow, RAUC is also used pretty commonly. And then there's one called Mender from Mender.io. The last one is somewhat commercial. So Mender do a free open source version, but they also sell additional bits for a fee. The other 2, Software Update and RAUC, are totally free. Okay, so let's kind of solve the update problem. What about security? So we want secure devices. We've got all these devices scattered around our homes and factories and workplaces. And, you know, there are cameras, there are projectors, there are entry systems to various things. We want to know that nobody's spying on us, basically. So from an end user's point of view, I want to know that my device, my door entry system, is secure and that nobody can hack into it and open my door or capture pictures or images of whoever is standing outside the door or whatever. So we want security both from remote access, if it's an internet connected thing, and also from local. So the way this is normally implemented is by locking the whole system down so that you can't supply any updates except those supplied directly by the OEM as an over-the-air update or as a live update. So that means it's locked down also from you, the owner. It means that you can't modify it either. So we have secure boot. Essentially, this is a chain of trust, which typically comes all the way from the some encryption keys burned into the chip itself using so-called fuses. And then that encryption key is used to validate the bootloader can then validate the kernel, and the kernel can validate the root file system. So if you do it correctly, you have a chain of trust all the way from the hardware up to your operating system. And if you try and modify any one of those things, it's not going to boot. For user data, typically you would expect the flash memory to be encrypted, so nobody can come along and physically access your flash memory and copy your details. And the updates, particularly the over-the-air updates, we need to be sure that those are valid and that they're not from some third party who is sending an update to us, which is going to compromise our system. So the OTA images are signed by the manufacturer, so we can be sure they only come from the manufacturer. However, in my opinion, this leads to a bit of a problem in that once you've done all this stuff, who actually owns the device now? Not me, it's really the manufacturer who owns the device. And in some cases, that can be a problem. And the last thing I want to look at, I'm probably going to finish a little bit early here, but that's okay. I want to look a little bit at licensing. So this is something that, for reasons I can't quite explain, interests me. But the licenses have a big effect or a big impact on the software that we use. So licensing. So most of the stuff I'm talking about here is built using open source tools and open source code. So it's embedded Linux, it's systemd, it's GNU compilers. The whole thing is open source. So, yeah, good. Great. Can I see the source code? Maybe make some changes? No. That's not the way open source works. So simplifying dramatically here, there are basically two classes of licenses that apply to open source. There are the copyleft licenses, for example, the GPL. Now, the GPL license does ensure that you, as an end user, have access to the GPL components of the software running on your device. So that's nice. There are also a class of permissive licenses, such as BSD, MIT, Apache 2.0. So these are open source to the OEM, but there's no requirement for the OEM to make public the source code they are actually using. So they can take Apache 2.0, hack it around a bit. We never get to see it. Permissive licenses are very popular with OEMs. Oh yes, disclaimer, I'm not a lawyer. Please consult your legal department to clarify all these details. So I want to drill down a little bit more, particularly with the GPL and GPL3. Sorry, GPL2 and GPL3. Because this is what everybody talks about. Again, simplifying hugely. The main issue with GPL2 is that the license says that if you link your code, your proprietary code, with code that is licensed using GPL, then the new entity becomes a derivative work of the GPL code, and therefore the GPL applies to the whole thing. So this is the kind of virus open source licensing that Steve Ballmer referred to 20 or 30 years ago. This is not necessarily a problem. So there is another license called the lesser GPL or LGPL, which is predominantly used for libraries. And the key thing about the LGPL is it doesn't have this derivative work thing. So long as you are linking your code with LGPL library code, everything's fine. And to be honest, that's what most people do. So conclusion, from my point of view, I think GPL version 2 is not a problem, so long as you're careful. GPL 3 is a little bit more tricky. So there's a clause in GPL version 3 which talks about providing installation information for user products. In essence, it says that if you have a product which contains binaries compiled from GPL3 code, then you, the manufacturer, must supply installation information which would allow an end user to replace those GPL3 components with new modified GPL3 components. In other words, it must be possible for an end user to modify the code running on a typical embedded system. And this obviously is incompatible with the concept of secure boot. With secure boot, the images are signed by the manufacturer using keys. Those keys are not provided to end users, obviously, and therefore the only people who can update that device are the manufacturers. So that violates the GPL3. And so this has caused what I call a GPL backlash, which has been kind of gathering pace over the last, I don't know, 6 or 8 years. So first, most legal departments will run a mile, 1.6 kilometers, from GPL. So legal departments do not like GPL version 3. And yeah, there are reasons for that. But the message now is that all GPL is bad, which is not true, in my opinion. And so a lot of organizations have put out the message that GPL is bad. We don't want GPL in any of our products. We want everything built using permissive licenses. And this leads to some slightly weird things. So I do a certain amount of work with Android. Android has this condition. So Google don't like GPL. They have a rule that says no GPL in user space. And so if you look at Android, it's kind of weird in many ways. One of those ways is it has a non-POSIX C library. The C library is called Bionic. It's a terrible C library. It's the worst C library you've ever seen. It's missing a whole load of functions. Some of the functions that are implemented don't work the way that they're meant to. And it means that you can't just take some existing code, which works with, say, glibc, and expect it to compile under Android. It's not going to work. So that is a barrier. And to be honest, I think that costs Android quite dearly because it means they need to re-implement whole bunches of stuff. But that's the kind of consequence of this blanket no GPL thing. Little side note down here at the bottom, if you do look at an Android phone, there is some GPL2 code in there. It's called Linux. And they say, oh, that's fine because Linux is not user space. This is an artificial distinction in actual fact. What it really means is they don't have an alternative to Linux. And so they're kind of stuck with it. I'm sure if they could, they would happily implement their own kernel.
Can you just say Linus made an explicit exception that GPL license do not apply for system calls?
Correct. So the question is, does GPL apply to system calls to Linux? No, it does not.
And that's why they allow it, because you don't get the GPL contamination by using the Linux kernel because it has an explicit
Yeah, indeed. So as with all Linux systems, you can have proprietary code calling Linux because there's an exception there that says The call chain from Linux upwards does not propagate the GPL. In other words, I can use Linux system calls from proprietary code. That's all fine. And, that's been the same for a long, long time. So I've been watching this GPL backlash kind of gather pace over the last, I don't know, so many years. And it seems that GPL is kind of being sidelined now because nobody likes it anymore. And yet it is a very good license. It's the only license which guarantees that we get to see the source code. If everything is permissive licensed, then everything goes into little silos or big silos where they hack it around in some ways. But we don't get the kind of community. We don't get the feedback. We don't get the scale where everything is developed as a group rather than people developing things on their own and hacking things around a bit. So that's basically what I wanted to say. So, like I say, this is a little bit shorter than I had intended, but it does mean we can go and get ready for the party sooner. So just a quick finish off then. Call to action for everybody here. Take an interest. Take an interest in your devices. Take an interest especially in the way they're licensed and the way that you interact with them. How much control do you really have over the things in your home? And where possible, try and choose open source, open hardware. In other words, hardware that has an open designs. And open data, in other words, data that is not locked away behind firewalls, or paywalls rather. Don't get locked in. And then join in, get a Raspberry Pi. Get a Raspberry Pi, start hacking, make those LEDs flash on and off. And that is quite literally it. So we have plenty of time. Does anybody have any questions? I think I have a microphone here. Does this microphone work? Hello? Probably not. Unfortunately, we seem to have lost our audio engineer. See if that can work.
Hello.
Oh.
Does everyone hear me? It's less of a question, it's just an addition to GPL. I think also one of the misconceptions of why legal departments steer away from GPL is that they think if you use the GPL code in your device, it means you need to immediately make it public, which they want to refrain to. Whereas in fact, the GPL says that you only need to make the source code available to your user. So technically, you can't just go and demand source code, GPL source code from a random vendor unless you buy a device from them.
Correct, yeah.
So, and they don't have to publish it openly. They can only just give you a CD with it, and that's it. And this is why, like, some people are afraid. They think they need to immediately publish it, but they don't have to actually.
But also, I'd like to emphasize that that part of the license only applies to the GPL components. So the worst case is you need to publish some GPL code, which is already free. I don't see that's a big problem. And people have been coping with this for many, many years now. Anyone else? Oh, couple.
For a project we tried to use a copy on write file system instead of A/B partitioning.
Okay.
So we snapshot our system, perform the update, and if it's successful, then we mark that snapshot as bootable.
Cool. That sounds good.
Have you seen any progress with that in industry on embedded devices?
Sorry, I missed the first bit. Which file system is that?
It could be ZFS, it could be ButterFS, it could be the newly merged Bcache FS.
Yeah. So the idea of snapshotting file systems has been around for a while, and ButterFS is probably it's the one that I've heard about the most. It seems that whenever somebody tries to use it on a real product, it doesn't quite work. It seems not to be sufficiently robust as a technique just yet.
That would be true with ButterFS, I would say. But the two other ones are pretty good.
Okay.
Yeah.
Okay, well, that's good to know. I mean, the answer is I don't know that many people using, or I don't know any people using that at the moment. But I think it's an interesting and way to go. AB updates are great, but it does mean you waste half your flash memory. So that's good. Yeah. Okay, thank you.
It's related to the GPL licenses. And one thing is the obligation to give away the source code.
Mhm.
But the other one is related to the obligation to let the owner change the component, recompile their own version of a library and install that.
Yes.
Isn't that also applies to LGPL to some extent, to my understanding?
That would apply to LGPL version 3 and GPL version 3. It does not apply to GPL version 2 and LGPL 2. Which is why the GPL 3 versions of the licenses are problematic. I mean, in my opinion, there are ways around this. I don't see there's any great problem with allowing the end user to update their devices, so long as they're doing it and are aware of doing it, and maybe you void the warranty or something. I'm happy with that. But what it comes down to is that the security should be applied at the application level, not the device level. So one of the reasons, in my opinion, that devices are locked down in this way is because the application security is terrible. So the solution is to lock down the entire device so you can't modify it in any way. And therefore, it doesn't matter if the application is rubbish, nobody will notice. So I would advocate in the future, we should try and design secure devices, secure applications, rather than locking the device down. And this happens to your laptop or your whatever. I can quite happily watch streaming media on here from Netflix or whoever, and nobody has a problem with that. Even though I have sudo access and you have permissions on your Windows systems, admin permissions, that's fine. But if you try and do the same thing on your Android phone, there's a little thing called safety net pops up. And safety net says, oh, this device has been rooted. It's not running an official Android operating system, and it just blocks it out. In my opinion, that is going too far. And in my opinion, that indicates that the writer of that application maybe didn't get the security right at the app level. And yeah, that's my theory. Okay, anyone else?
And just to switch over from licensing, I'm interested in more. Can you elaborate? You mentioned several when we do AB updates, right? You're saying like, well, we switch from a slot A to slot B when we deem that like the update is okay.
Yeah.
Like, what are the underlying technique? Like, at which point do we deem it? Like, what I mean is like, it can be my kernel can boot in the update, but then the root file system is broken, or system D starts, but a network daemon is broken. So at which point in the device boot we can say, yeah, this update is good, and we can like mark slot B as a new slot.
So the first level is that you can check some of the update and make sure that the update itself was correct. In other words, it's the same image as was sent out or was on the USB stick that you applied. That doesn't guard against the possibility that the operating system itself is broken. So maybe system D doesn't run. In which case, you need what's called a boot count. So within the bootloader, you have a boot count. Every time you boot, you increment the boot count. And every time you boot successfully, you decrement the boot count. So you increment it in the bootloader, you decrement it in the operating system. If everything's going fine, the boot count should always be 0. But if after a number of reboots, you find the boot count has incremented, typically 4 for some reason is used. So after 4 failed boots, we say, this is not going to work, and we go back to the previous version.
But you said boot successful. So at which point do we decrement then the boot count? Inside the
Well, that's an interesting question. How do you know what is success? I guess that's kind of different for each implementation, but typically it would mean that you've booted to the point where you can run applications of whatever sort. Not necessarily that you started any particular application, although you could code it that way. But just so you've got to, in Android terms, you've got to the launcher screen, and that probably indicates it's doing okay. But that has to be different for each operating system.
And all the tools you listed, they kind of like flexible on this, or?
Yeah, basically, you just call a library, a function call in a library to indicate that we have booted successfully, and yeah, off you go.
Thank you.
One more question about software update. You
Mhm.
mentioned 3 different types or 3 different implementations.
I did.
Do you have any recommendations on when to use which one, or what's the differences?
I'm not sure I really want to get into being partisan to that extent. I mean, all 3 that I mentioned, Software Update, Rauk, and Mender, they do the basic stuff. No, you need to choose one of them. But from an implementation point of view, they're more or less equivalent. So each one will do as well as the other, I believe. I guess the advantage maybe of Mender is they do have an out-of-the-box experience, which includes not only sending the updates, but also doing what's called fleet management. So fleet management is you've got a fleet of devices out there, and you want to schedule updates to certain numbers of them at certain times. So you don't want to update everything all at once. So you kind of schedule it, so we'll update these machines one day and these machines the next day and so on. So Mender has an out-of-the-box experience for that. You can do the same thing with the other 2, based on a package called Hawkbit. So, which is an open source thing. It's just a little bit more hand assembly to make that work. Okay. Right. Well, it looks like we're out of questions. So thank you all very much for listening to me. And yeah, we're done.